Piping vibration, cavitation, understanding vibration effects caused by fluid bubble collapse. Significance of cavitation in piping vibration. Cavitation is a critical phenomenon in fluid systems that significantly impacts piping integrity and operational reliability. It occurs when local pressure within a liquid drops below its vapor pressure, leading to the formation of vapor bubbles. These bubbles collapse violently when they encounter regions of higher pressure, generating intense localized shock waves. This process produces noise, vibration, and severe mechanical stress on piping components. Cavitation is particularly concerning because it accelerates fatigue damage, erodes material surfaces, and compromises system efficiency. In industrial applications such as oil, gas, and chemical plants, cavitation-induced vibration can lead to catastrophic failures if not properly managed. Understanding its mechanisms and implications is essential for engineers to design robust systems and implement preventive measures. The phenomenon is transient and highly dynamic, making it difficult to predict without detailed analysis. Its effects are compounded in high-pressure systems, where sudden pressure drops occur frequently, such as across valves or pump impellers. The short time to failure associated with cavitation underscores its importance in vibration management strategies. Mechanism of cavitation, formation and collapse of vapor bubbles. Cavitation begins when fluid pressure falls below the vapor pressure of the liquid, typically due to high-velocity flow or abrupt changes in geometry such as valve throttling or pump suction. Under these conditions, vapor bubbles form within the liquid, creating a two-phase mixture. As the fluid moves downstream to regions of higher pressure, these bubbles collapse almost instantaneously. The implosion generates microjets and shock waves with localized pressures reaching thousands of psi, causing pitting and erosion on metal surfaces. This repetitive cycle of bubble formation and collapse induces high-frequency vibrations that propagate through the piping system. The dynamic nature of cavitation means that its intensity varies with operating conditions, including flow rate, temperature, and pressure differential. In addition to mechanical damage, cavitation reduces pump efficiency and can lead to flow instabilities, further exacerbating vibration issues. The violent collapse of bubbles near solid boundaries is particularly destructive, as it concentrates energy on small areas, initiating cracks and accelerating fatigue failures. This mechanism explains why cavitation is a leading cause of vibration-induced fatigue in process piping systems. Conditions and locations leading to cavitation, common causes and high-risk areas. Cavitation typically occurs in regions where fluid experiences a sudden pressure drop, such as pump suction lines, control valves, and orifice plates. Centrifugal pumps are highly susceptible because the impeller design can create low-pressure zones at high rotational speeds. Similarly, throttling valves and flow control devices introduce abrupt changes in velocity and pressure, fostering cavitation conditions. Factors influencing cavitation include fluid properties, density, vapor pressure, operating temperature, and system pressure differential. High-temperature fluids have elevated vapor pressures, increasing cavitation risk. Multiphase flows and flashing conditions further complicate the scenario, as they introduce additional vapor formation mechanisms. Poor system design, such as inadequate NPSH, net positive suction head, in pumps, exacerbates cavitation. Inadequate pipe support and improper valve sizing also contribute to localized pressure drops. Identifying these high-risk areas during design and operation is crucial for implementing preventive strategies. Engineers must consider the entire operating envelope, including transient conditions like startup, shutdown, and emergency depressurization, as these often present the most severe cavitation scenarios. Impact on piping integrity and system performance, effects and consequences of cavitation. The collapse of cavitation bubbles generates intense localized forces that lead to material erosion, pitting, and surface fatigue. Over time, these effects propagate cracks and cause structural failures in piping components, valves, and pump casings. Cavitation-induced vibration accelerates fatigue damage, particularly at welds and small bore connections, which are already stress concentrators. In severe cases, failures can occur within hours of cavitation onset, posing significant safety hazards and environmental risks. Beyond mechanical damage, cavitation reduces hydraulic efficiency, leading to increased energy consumption and reduced throughput. The noise associated with cavitation is another indicator of its presence and can reach levels harmful to personnel. From a reliability perspective, cavitation shortens equipment life and increases maintenance costs. Its unpredictable nature during transient operations makes it a critical factor in risk assessments. The combination of vibration, erosion, and fatigue underscores the need for proactive design and monitoring strategies to mitigate cavitation effects in process piping systems. Design and operational strategies, preventive measures and best practices. Preventing cavitation requires a combination of design optimization and operational control. Key strategies include maintaining adequate net positive suction head, NPSH, for pumps, using anti-cavitation valve trims, and staging pressure drops across multiple devices to avoid abrupt changes. Selecting valve types that minimize turbulence and pressure recovery, such as globe valves with multi-stage trims, can significantly reduce cavitation risk. Flow smoothing techniques, including long radius bends and streamlined fittings, help maintain stable pressure profiles. In systems where cavitation cannot be entirely eliminated, material selection becomes critical. Components exposed to cavitation should be constructed from erosion-resistant alloys. Operational measures include controlling flow rates and avoiding rapid valve actuation, which can trigger transient cavitation. Monitoring systems equipped with vibration sensors and acoustic detectors can provide early warning of cavitation onset, enabling timely intervention. Incorporating these preventive measures during the design phase and maintaining strict operational discipline are essential for minimizing cavitation-induced vibration and ensuring long-term piping integrity.